We left off here yesterday with the idea that the absolute value of the remainder can be called the error. And this formula gives us the ability to say that the error must be less than. And again, I would like to make an edit to this formula. I want to call it just big M multiplied by the absolute value of x minus a to the n plus 1 power over n plus 1 factorial. Did I tell you yesterday what M is?
Maximum value taken on by the n plus 1 derivative for values between a and x.
Okay, M is the max value
taken on by the n plus 1 derivative.
Taken on by f of n plus 1 derivative
for values between a and x.
Okay, let's call that for C, where C is in the interval, or is between A and X. Yep. So this gives us the ability to say, given a Taylor polynomial, how good is the estimation? Okay. Here it calls it the remainder estimation theorem. It goes by another name on the AP exam, and it's the Lagrange error. Okay. So we know that we can represent functions as infinite series. If we don't do it infinitely, if we do it finitely, then we know that the polynomial, the truncation of the infinite series, is a reasonable estimator, and this tells us how good that estimate is. Right? Everybody see it in action? All right, let's do it. Here we go. Oh, I don't want to do it this way. Come on. Change slide. There we go. This is what I want to do. So, here we have a function, natural log of x plus 1. Now, if you were in the 1800s, you'd say, I need to figure out what the natural log of 2 is. Now, the natural log of 1 1/2. You might use this polynomial in order to do that estimate. In fact, I misspoke. I said 1 1/2. I actually can only use this right around 0, because this series is centered at 0. And actually, since this is based on the geometric series, it's only this series only converges for numbers between -1 and 1. So let's investigate this. Let's investigate this 2 ways. Let's use that remainder estimation theorem and calculate how big the remainder can get. And then let's actually compare the natural log function to this polynomial estimate and see how close they are. So, in order to find out how big the error might be, we'll need to say, oh, it's going to be m multiplied by the n plus 1 derivative for some value x divided by n plus 1 factorial. So let's fill in the blanks. Let's start with m. In order to find m, we're going to have to know what the n plus 1 derivative is. Well, I suppose we're going to have to calculate some derivatives. Let's go and apply our Taylor series, Maclaurin series skills. Nth derivative at x.
How much earlier did Maclaurin come up with that?
I don't recall. I actually don't know my math history very well. So I don't
It's
know.
not there, Maclaurin.
I know Taylor's there. Brooke Taylor's up there. I don't know. Why don't you take a look to see what Maclaurin is while I finish writing this table. The zeroth derivative is the natural log of x plus 1, is it not? The first derivative,
Negative 1 over x plus 1.
I don't think there's a negative there.
It's 1
Oh,
over
I'm thinking about the second.
I think it's 1 over 1 plus x, which I think I would rather write as 1 plus x to the negative 1 power.
The next one's with the negative 1.
Okay, and then the second derivative is going to be negative x plus, or 1 plus x to the negative 2. When can I stop? If this polynomial can be written as P2, polynomial that goes up to order number 2, and I want to do the remainder theorem, I need to go one beyond that. So if this is order 2, I'm going to need to know what the third derivative is.
It'll be 2 times.
There we go, indeed. And now I've got a question for you. In order for us to get that m, I need to know the maximum value that this expression takes on some interval. First of all, I need to know what interval.
The absolute value of x is less than 0.1.
So we want to get the maximum error where we're within x is between negative 0.1 and positive 0.1.
Yep.
Okay, so the range of values I'm looking at is x between negative 1 and positive 1. Next question. Okay, that gives us the range. How am I going to find for what value of x that this expression is at its largest? Or I should say the absolute value of that expression. It's the maximum in absolute terms. Should we graph it? Yeah, let's graph that and see what happens.
It's like chapter 2 over.
It is. I guess what we could do is we could take its derivative. But let's oh, did I close the calculator? I sure did. Let me get the
You're allowed to use buffers in your test.
on certain portions of the test.
On the test that's going to be given to you.
Possibly. Possibly. There we go. So let's put in that function. What was it? 2 times the quantity, 1 plus x. Let's try that again. 2 times the quantity, 1 plus x to the negative 3, caret 3. And let me graph that.
Negative 3.
Oh, did I not have it right? Oh. So, second insert negative. Is that better?
Yep.
Zoom standard. You know what? I don't think I need to look at this in a standard viewing window. I think I need to look at it only on the interval that I'm interested in. From negative 0.1 to positive 0.1. Okay, window, negative 0.1 to positive 0.1. And then what I'm going to do, is it negative 0.1?
No, for the scale.
No, what I'm going to do is this. Zoom. So zoom. What's fit? 0? I just discovered this earlier today. We're about to retire these calculators. I just found this feature. If you set up the x boundaries, then it'll only set the y values so that the graph will fit in there. So what do you think? For what value of x do you think that third derivative reaches a maximum value?
Whatever the top line.
Up on, what's that?
That's not really what calculator is. Like, why are you trying to?
Because the new ones are so much cooler.
What are you gonna get?
Unless you're Eric,
Are you
you
gonna-
hate
Are you
technology.
gonna get, or like, is Bert
I-
gonna get
I do.
inspired or something? Like
Yeah,
that?
that's the plan.
Ridiculously expensive.
What?
We had them for right now.
Yeah, there you go.
We've had them for like 3 years.
See?
What the heck?
Yeah, we have one too.
Oh, look. See?
Why is Berkeley so bad?
We have Aspire, but not like NCS.
Well, we only have like one class. and then
So anyway, so yeah, we're gonna do this. Anyway, so upper left is what's Ethan saying. So what is the maximum value of the third derivative? How about I go second calc value, and we're at -0.1. So it looks like the largest value that this function takes on is 2.743. 2.743. Okay, let's take that value and bring it back to our screen. 2.743 multiplied by
F of and F.
I'm sorry, there's something wrong here.
Shouldn't it be x minus a?
Yeah. This isn't,
Minus a.
yeah. It's like, isn't this the n plus 1 derivative? It is.
Yeah.
This is supposed to read x minus a to the n plus 1 power. Now, a is in this case,
X minus a should be in.
oh, and this should be in absolute values.
Yeah.
Everything in here should be producing positive numbers. Errors are only positive.
Got it.
Okay? So, what is A? A is the center of our series, and in this case it's 0. What is X? X is the largest value in the interval of our interest. Oh, sorry. What we want this thing to create a large value, as large as possible. So the interval that we're interested in is 0.1. And then we'll take all of that. Oh, we'll take this and add to the n plus 1, which is going to be 3. Well, this is,
Wait, sorry.
2.
My question is, why did we go up to 3?
well, because the polynomial that we're using to estimate the function is the second order.
So, you have to go
So
up.
we got to go one higher.
Okay, got it.
All right. So we're taking this up to 3, and then we're going to divide by 3 factorial. Gosh, I hope this works.
I don't even know if it works.
Well, so I'll show you in a second. We're going to actually, graphically, we're going to see if it works. You ready? I need someone to give me that value. No, Eric, you can't use your calculator because you hate technology.
Okay.
You can't even look at the
Hands.
board right now. You're not allowed. It's technology.
Don't pick up that pencil.
Do the work.
At what point do you call an end?
I draw a line at technology that involves computers.
It's
Calculator's a computer. One more time, Shayna. 0.457. Does anyone confirm that number?
I can't use technology.
Well,
Can anybody else confirm that number?
I hate technology too.
Thanks.
Wait, you want me to run the 3 decimal places, right?
That's 3 decimal places.
Oh, wow.
Yeah.
Oh, there's 3 too.
Did you get it?
Kind of.
Oh, wait, never mind.
Never mind.
Yeah.
Yeah, I
Oh.
forgot. 2.1.
Oh,
Shush.
It's 4.5, right?
Point
See?
oh, oh,
technology
4,
doesn't
5,
like
7.
us.
I think I messed
So
up.
I like in your
Okay, I'll
head,
do
that's
it.
better.
Kind of goofed.
Okay. 2.743 times 0.1 cubed.
I got
Oops, I gotta get out of that screen. Okay,
Negative 4.
2.743 times 0.1 cubed, and divide that by 6.
571.
That's what I got.
Yeah, that's right.
You didn't
Okay.
get 4.
So it's not 0.457,
Yes, right.
it's 0.0004751. Okay.
Tiny error. Too close.
Boy, that suggests for that range of error that this polynomial is a really good estimator. It gets you down to the thousandths place. Now, can we prove that it's true? Okay, here's how we're going to try to prove that it's true. I'm going to I'm going to get rid of that. I want to put the real function in L1. Natural log of 1 plus x, right? And then in y2, I want to put the estimator function. It was x minus x squared divided by 2. All right? And let me graph those two.
Oh, jeez.
What's wrong?
It just says C.
What should I do to
It's
fix
not
this?
Showing up.
Not bad.
What should I do to fix
Zoom fit.
Zoom fit. Zoom fit.
Don't, you have to change the...
No, the x bounds are still -1. So there's the original function.
Where's the other function?
Was they right on top of each other?
The
Yeah.
same thing.
Here, let's do this, just to emphasize it. I'll make
Yeah,
that
fat
thick line.
line. Fat
Here we go. That's the natural log function. Drawing, drawing, drawing. And there is the polynomial function. Drawing, drawing,
Same
drawing.
thing.
So they look. So we said that the error was really, really small, and this would suggest. You know what? Let's see if we can actually see the difference in the error. I'm going to do one more change here. I'm going to turn off this plot. I'm going to turn off this plot, and then y3, I'm going to plot. Ready? The absolute value of y1 minus y2.
What do we have in mind?
Well, and y1 is the real function, and y2 is the estimator function. So the absolute value of that difference is what we call the error.
But what was the point of finding the error? Just to prove that they were really close?
Well, it,
As in we could have
no,
done
it's
just
okay.
graphing.
The reason why we do this is that from a computer science standpoint, if you're writing a program that says I have to return the sign value to so many precision spots, it's nice to know how far you have to go out. So that calculation tells you how many allows you to check to see that theoretically we're going to be beneath that error bound.
So, but basically it's guessing. You don't never like, it's like, oh, I'll pick this random number and hope the error is.
No, we're not guessing. We're actually being able to calculate an upper bound of the error.
No, I know, but we don't know what the error is going to be like until you do that term, the error for that term. But you have to pick the term. Like if you go to the third power or the fourth power, like how do you know?
Well, for the people who design, let's say, our calculator, they know that they have to produce a value of sign that's accurate to 13 digits.
Yeah, but I'm saying I don't know where the.
And since the values of sine and cosine are cyclical, you know that essentially every number that they could possibly ask can be mapped into the space for sine, let's say, between negative pi over 2 and pi over 2. So there's a very strict interval then.
Okay, but it's still good.
Okay. Well, anyway, let's take a look at the graph of the error. Here's the graph of the error.
I'm just trying to understand it.
Oh wait, it's not graphing anything.
Oh, zoom fit?
Zoom fit. Zoom here is the error associated with these two representations of that function.
Yep.
When is the error maximized?
At
Point one.
0.1.
At negative 0.1? So let's go. Second calc, value, negative 0.1. And the value of the error there
Small number.
is 0.00003. Our calculation said that the error must be smaller than,
But what I'm saying is they gave you the term. Like if they didn't give you the term that to derive it to the power of that power, like we were deriving to the power, the third power. But what if they didn't give you? How do you know like where you should stop? Because that's guessing. You're like, well, I'll look like this.
okay,
Is that a question or a statement?
That's a question. Like, do you understand what I'm saying?
well, let me see if I can restate your question
Okay.
in a way that I can answer.
Okay.
So your computer program is running and it's trying to estimate the value of a function using some sort of infinite series.
Mm-hmm.
And it goes along, and it's like, I got 3 terms now. Am I good enough?
Oh, but that's computer. What about us? Sorry. Like if you right now, if you ask me, like, can you do the error to like point like 001, and it's like, how do you know which term to pick to like try to get it below it?
I think it works the other way. I'll say how far, and then I'll ask you how close to you is your answer.
Okay.
All right?
Yeah.
Does that seem fair?
Yeah, but I'm just like I was wondering the other way around. But like,
Bless
bless
you.
you.
Oh, sorry. All right. So I think I understand. It's like, at least if you're asking the question, how is this going to be tested? It's almost always going to be tested. I'll tell you how far, and then you tell me how close your answer is to the real answer. You're not going to tell me the real answer. You're going to tell me how good your estimate is based on this theorem. All right. So, last thing I just want to point out is this value that we just got, 0.000036, consistent with this calculation. It's the real error is less than this upper bound. This doesn't tell us what the error is. It tells us the error is no bigger than that. Is that okay? All right. I want to try this again. Let me see what the next one is. Yeah, here we go. Here's a function, cosine of pi x divided by 2. I would like to use the 4th order Taylor polynomial to estimate the value of this function at x is equal to 0.2.
Okay, so you do n and the nth derivative of x of f at x.
Okay, so you want me to write that down. N,
4,
0, 1,
0, 1, 2, 3, and 4.
f,
Stop. Why 4?
because it says fourth order.
But when we do the error
Yeah,
calculation,
it's fifth order then.
we need to go one more. All right. So functions derivative at x,
First one is the zero derivative, which is cosine.
just the function itself, cosine pi x over 2.
And then we take the derivative of that. which
Okay. Why don't you
is-
popcorn someone?
Okay, Ethan.
Gotcha.
Take the derivative of that.
Take the derivative of cosine. Yep.
I'm good. Take it.
negative
Yeah.
Is it negative? Yes, it's
Yes,
negative.
Negative.
So
sign.
we begin with sine.
Pi x
Does it have a
over
sign?
Pi
pi.
x over 2.
So negative pi. But it's not
Is there a chain rule?
Yes.
negative pi. Over 2.
Ethan, can you confirm that one?
I can't.
Okay. Can you help me? Okay. So that's the first derivative. How about you help me with the second derivative?
You will get negative.
Good.
Negative cosine.
No, I'm, yeah, pi over 2 squared.
Pi over 2 squared.
So
Very close.
Pi squared is the,
Pi squared over 2 squared. Excellent.
cosine of pi over 2.
Can you guys confirm that?
Yes.
Popcorn someone. Negative? Because we're taking the derivative of cosine. And the derivative of cosine is
Positive sign.
okay. Did I miss something?
Yeah, cube.
Oh, cube on the bottom. Okay. Popcorn someone, Matthew.
Negative pi to the power over 32, which was 2 to
To the fourth is 32?
Oh my god. Okay, just
No.
yeah, never mind.
16.
16, sorry.
Okay, and this is,
Sine.
wait, the sign, wait, is this positive still?
Yeah, it's
Yeah,
positive.
cosine. Your positive is positive?
No.
Oh, yeah.
Wait, am I
Absolutely,
doing
ah.
fourth power? Sorry, I was doing fifth. That's why.
Oh,
I was
okay.
doing fifth. That's
So
why.
go ahead and give me the fifth. Pi over
Okay.
5 over 32
Yeah, sine pi. Okay, it's negative 2.
and negative
Sine
sine.
pi is negative 2. So sorry, it's negative. It's weird.
Yeah.
we just-
Okay, so we did that. That's great. And if we're trying to calculate the error, that's the one that we're going to need, right? But can we go back and answer the question?
Yeah.
Find the Taylor polynomial of the fourth order for this function. Have we done that yet?
Not
No.
Well, we're on the way if we're going to be using the big tabular method. But we don't necessarily have to use the tabular method to calculate the Taylor polynomial.
Use the CAS.
It is true that on the CAS you simply can say, give me the Taylor polynomial for this function. That is true. But I was thinking about a middle ground.
Wait, do you plug in point 2 in there?
We're not,
Plug it in.
We're not doing that?
okay, we are going to do this. We are going to calculate the cosine of pi times 0.2, but we're only going to do it approximately.
So we're gonna do it at x equals 0, because it says use it to approximate the value
Over
of
10.
x equals 0.2.
Over 10.
Okay, we are going to, in order to approximate it, we are going to produce this fourth order polynomial.
Okay.
All right? We have yet to produce the fourth order polynomial.
Oh.
I'm going to help you guys out.
Thank you.
Cosine of x is equal to 1 minus x squared over 2 factorial plus
X to the fourth.
x to the fourth over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. We agree there.
Yeah, and then you have to do pi over 2.
Okay.
Over 6.
Based on that starting point, which you've all memorized by now, can you tell me what the function cosine pi x over 2 is going to equal? 1 minus
Squared over pi over 4 times 2 factorial.
X squared over 2 factorial.
No, but you missed 2 factorial.
oh,
2 factorial.
square. Okay, this squared is 4 times another 2. It's 8.
So 8.
Okay, plus because we got to get at least to the fourth order.
Pi.
Pi squared.
Nope.
Pi
No, pi to the
4.
fourth.
Pi 4 over.
X to the fourth.
X to the fourth is 16 times 16 times 4 factorial.
Which is
Something.
another
Calculator.
384.
384
That's the same thing.
There you go. Yeah, because.
Plus 24.
minus
There you
dot
go.
dot dot.
You're doing too much. Swap the x.
And that's x times x to the
Yeah.
Four.
4.
Like that.
Okay.
Okay, so
Wait,
point
now
2
we're going
comes
to
with 7 for him.
Okay. Here's what I want to do now at this point. We've got this Taylor polynomial that represents that function, right? Yes. All right. So I may say that cosine of pi times 0.2 over 2 is approximately 1 minus pi squared over 8 times 0.2 squared plus pi to the 4th times 0.2 to the 4th divided by 384.
But when it says go to the 5th power, how do you
We're
do
going
it?
fourth.
Plus,
Fourth power. Fourth power.
like a remainder of the error.
We have to go to the 5th.
What's that?
No. She said, like, no. It's, so we said then, this is the Taylor polynomial, right?
That's the Taylor polynomial because I didn't do dot dot dot. We
Yeah.
stopped it. We truncated.
So this is not the error part, right?
This is not the error part
Okay,
yet.
then we're going to the 4th. Yeah.
Because I'm trying to answer the question.
Okay, another question. What if it was sine and they asked to the 4th, but since it's odds, what do you do? Go to the next term?
No. Then you could stop. You could stop at the 3rd power because the 4th power is there. It's just times 0.
Okay.
All right. But they typically won't ask you that. They will say, "Give me the first 4 non-zero terms." So they try to get away from that vagueness of language. Okay, calculator. People, what is it?
I don't know, I'm not allowed to use it.
I have to see. Oh, yeah. Too much.
Will not be pulling your back.
Gotcha.
I have to get it out. Someone will get it before me, so what does it matter? I like the old movie right now. Even read. I don't know.
He may be playing block.
Is that Bottude, man?
I wish.
You have Bottude?
What game is that covered?
Oh, boy.
Oh, actually, Josh,
Okay,
had
point
Mario.
951 then.
Are we sure this time?
What is?
0.95105.
Wait, are we
Point
allowed?
951.
One.
Are we
One.
allowed to put the 0.2 on top of the fraction bar? The numerator,
That's nasty.
Is that okay?
Yeah, it's fine.
Okay.
Beautiful.
Doesn't-
All right. So there's our estimate for the value of cosine at that place. My question is, now that we've used it to approximate it, how close is that answer?
Random question.
Very,
Well, let's figure it out.
yeah, let's figure it out.
The remainder theorem says
Should be 1. Should be close to 1. So 1 minus 1
the remainder theorem says
Don't agree.
that the absolute value of the remainder must be less than
Or equals to.
The
Times
biggest
x
thing.
minus a, absolute value of x minus a,
Plus one.
the n plus 1.
So we have to figure out what the
Plus
biggest
one.
thing is.
Okay, now here is a seeming contradiction that I'm going to resolve. Are you ready?
Sure.
Yeah.
So what we end up saying is, in order to find out what the maximum value of the 5th derivative is, we've got to be able to find the value of sine. Wait, so in order to find an estimate for cosine, we've got to find the value of sine. We have to have enough computing power to find out what the sine is, so we can estimate the value of cosine.
Uh-huh.
So
Do you
you're
see the
estimating
problem I'm
to-
hearing
you're
there?
estimating to estimate. Is that what you're
No, I'm estimating.
So you're saying
I'm not estimating here to estimate there.
This
No,
or shouldn't
so-
it be 5 plus 1 and 5 plus 1 factorial since it's n times absolute value of x minus a to the n plus 1?
It's a 4th order. So we're going one bigger.
Okay.
All right?
We'll run a limb here and say.
So ready? Here's how we do it with sines and cosines. I'm not going to calculate exactly what that sign is.
Verdict.
I know a lot about sines and cosines.
They
I know an
between
absolute
negative
value,
one
they
and
never get any bigger than
One.
absolute
one.
value of one.
So why don't I just use that as my maximum value of any derivative in this case? Because you know
That
what?
is one.
It's a worst case scenario. When I see a sine or a cosine as my n plus 1 derivative, I'm going to maximize it at 1. Now, what does that mean? It means my error calculation may be a little high, but at least I can do it. All right, multiplied by, okay, in this case, a is 0. What am I going to put in for x? 0.2. Divided by factorial.
I'll even do it.
So I think this is going to be a pretty small number.
Yeah, negative,
0.008331.
One more time.
0.008331.
That's not what Katya's got.
Wait,
Zero.
let me look at it first.
Wait, I got 2.6.
Just kidding.
I got
did it wrong.
2.6 E.
Yeah, I did it wrong.
Yeah, me too.
So negative 6.
Yeah.
My bad.
So 0.0000026.
My bad.
That's a really small error.
Well, 2.7 technically, if you want to round it correctly.
267.
He went around it correctly.
No, I like to run it improperly. That's how I roll. All right. Now, let's see if we did everything right.
Mine is giving me 3.
Oh, yes.
So what?
The baby torture problem.
Oh yeah, didn't I say?
Middle of Casa.
Were you like making express?
Nope.
Yes,
Alright.
yes. I actually commented on it too. Remember? I was like, this is illegal.
It's one of the most fun problems. All right.
Wait, I didn't take any stats there.
So, you took it last year.
Okay.
So, it was in last year's book as well. All right.
Totally
So,
fine.
here's what we said. You calculated the estimated value of cosine is 0.951. Let me calculate it to more precision. Pi times 0.2 divided by 2. There's the real value of cosine. You calculated at least the 3 digits and got the same number. Okay, now let's do the last part. Actually, you know what? I'm gonna put this in. I want to get more decimal places accuracy. 1 minus pi squared multiplied by 0.2 squared divided by 8. I think I did that right. Plus pi to the 4th multiplied by 0.2 to the 4th divided by
It's crazy.
384.
How was it going with
Okay, so the first number is the real value, the second number is our estimated value using only a 4th order polynomial. And then let me do this. This number minus that number. So the real error is 1.3 times 10 to the negative 6.
You overestimated, so.
And our error was 2.7 times 10 to the negative 6. So what did we see? We saw that again our upper bound of error seems to be consistent with these calculations.
Yeah.
Yep. Good? Good. All right. All right. See how much time we got left? 12 minutes?
Can't do it.
Can't do it?
We have 4
Are you
more
sure?
slides.
12 minutes? I mean,
4 slides in 12 minutes, 3 minutes per slide.
Okay. We're going to do a slight little change up. We're going to leave error estimation for a little bit now. This is a really typical AP problem. I want to make sure that you feel comfortable with it. Please find the Maclaurin series for this function. Now, there are two ways to do this, the hard way and the easy way. Which way do you want to do it?
Let's do it the easy way.
Easy way.
Oh, isn't
Easy way is to say, let's use prior knowledge. Yes?
isn't x plus 3x to the third over 3 factorial? Isn't that sine x?
It's two of the terms in sine x.
Yeah, the second and
Wait a minute.
So
Wait a
it's to the
minute.
third order
Okay,
of sine x.
so watch and learn. Ready?
Okay.
Let me rewrite sine. Ready? Let me rewrite it in its Taylor polynomial form. So there's my rewriting. That's exactly what sine is, correct?
And then you just cancel out x.
Minus x plus x cubed over 3 factorial. Then we switch over to the red marker.
And
Minus
Let me just change the color
Zoom.
of the pencil.
Zoom. And zoom. Zoom. So what is the Maclaurin series expansion of this function?
That.
All that's left over.
okay.
Easy?
Get her done.
Get her done. Now this idea comes up in a couple other times. For example, we have at various times done this problem. We did this in chapter 3 when we were looking at limits, right at the very beginning. We did it in chapter 8 when we did L'Hopital's rule. I want to look at this problem one more time, but I want to look at it as a Taylor series problem. Do you know what the answer to this problem is? Oh, it's such a good one to memorize. I don't ask you to memorize much, but this one's a good one.
0,
Five.
5, 1.
1.
Oh.
That's my next guess.
I said it first.
So if we did it using L'Hopital's rule, we said, oh, if I put in a 0 here, I get
Zero
sine of
over
0,
zero.
I get something indeterminate in the form 0 over 0. And if you do L'Hopital's rule, then you say the
cosine
limit
of x over
1.
1.
cosine of x over 1, and cosine of 0 is 1. So this limit goes to 1. But let's take a look at this problem, not using L'Hopital's rule, but look at it in terms of Maclaurin series. The limit as x approaches 0, and let's look at the series expansion for sine of x. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth, all over x. Oh, I wrote it in red, so I can't break out my red pen.
Bring out your black one.
Let me just switch the color of my pencil. Maybe those red.
Can we clean up that expression?
Yeah, just cut out
Yes,
X
we can.
from all the
One,
values.
just 1x?
Yeah.
Oh, that's all you can do.
Yeah. No.
We can do 1x from every single term on the top.
There we go. Say that again, one more time.
We can do 1x from every single term.
Well, I mean, I'm just worried that you're gonna do something like this, Brian, and you're gonna do this.
He's smart. Do that.
Because 14 divided by 2 is equal,
No, and then I cancel out the 12 and write the 6, you know?
okay, so you have to do every single term.
Yeah.
Okay, so when I said only one,
From each.
from each one, okay. So
Here's
I
a 1.
cancel that x, that turns this x into a,
1.
and this into a 2, and that into a 4, and that into a 6, so on and so forth. Okay, now the bottom is a 1, and the top is a polynomial where I can plug and chug. What happens when I plug my x approaches 0 into the top now?
It'll be 1.
1.
It's only thing that doesn't go away is 1.
Plus it's the one for cosine.
Yeah, it's the
Is it? No, it's not, because in
Oh.
cosine, the,
Oh, yeah.
the power and the factorial have to match.
And the
That's what I
sign.
thought.
Okay. So you okay with that idea? We can look at problems in a new way when we think about their Taylor series expansion. Yeah? Okay. Let me see what the next slide is.
Oh, jeez.
Why is
I don't wanna
equal
do this
sign-
problem.
Why is the equal sign on the inside of the parentheses?
Who knows? No, what it is, they want you to do the series expansion of this.
And get that.
No,
Oh.
no.
And that's what it is.
But that's really hard.
That equals to that.
So
This
they're
is equal to,
saying-
remember, this is the one that we keep on using
Why
whenever
do
we,
you give hints even though they don't match in the book?
yeah. So they're saying use this hint to do that expansion.
But the hint was completely wrong.
Oh,
for this
yeah.
problem.
Okay, so what does this hint look like? What is cosine squared?
Correct.
Well, cosine squared, which is equal to, and I rather read it as 1/2 plus 1/2 cosine 2x. So what I can say, it's 1/2 plus 1/2 times, and I can do the Taylor series expansion for cosine 2x,
So weird.
which
So
is
it's gonna be-
1,
Is it gonna be 1 or wouldn't it be
It's
2?
gonna be 1.
it's going to be 1,
1 minus 2x squared over 2 factorial.
2x quantity squared over 2 factorial. Is
Plus,
that right? Wait, stop, is that right?
Yes, that's right.
Yeah,
Okay. Minus, sorry, no, plus
2x quantity to the 4th over 4 factorial minus quantity 2x to the 6th over 6 factorial plus that.
Okay, and that is an expression that's totally equivalent. Now, what would probably happen here? Oh, you might want to distribute those 1/2s all the way through. And so I end up with 1/2 plus 1/2 minus 2x squared over 2 factorial plus 2x cubed x to the 4th over 4 factorial minus 2 to the 5th x to the 6th over 6 factorial, dot, dot, dot. Did I make, did I,
Wait, why is
did I make a mistake?
Find the 2. Never mind.
No, did I make a mistake? 'Cause
No. You're good.
I'm good? Because 1/2 times 1 is 1/2.
Yeah.
Yeah, you just reduce
When I
part of the 2 by
take
1.
this hit, it will take one of those 2 2's
Yeah.
away, leaving only one 2.
Oh,
Pretty good.
okay.
When I get to over here, one of these 4 2's are going to go away, leaving only 3 2's.
You're good, you're good.
All right. So that's not that bad. And then what do? Break out your black pen.
Change your colored pencil, Brad.
Okay. And the 1/2 plus 1/2 is just a big one.
Go.
Doing some business.
Stuff.
Just try that, isn't it?
Stuff.
Okay, that's.
All right. All right.
Didn't even know he was going.
So there's your assignment.
Yeah.
That wasn't that bad. I guess I have to wait till it's over. What is this?
Do we have to know that?
You can't just throw imaginary numbers.
Yeah, I thought we were
I
good.
thought we were done with this, right?
Yeah.
Wait, is this relevant to anything?
This is a road.
Actually,
Relevant.
I thought it was someone in this class that asked me why that was true. If it wasn't someone in that
No,
class,
no,
we're actually to the point I can explain why this is true.
Okay.
Do it.
Why?
You got 2 minutes.
I get 2 minutes?
Yeah,
Yep.
you have 2 minutes.
Okay. Every complex number can be written in the form a plus bi. Complex number's got a real
Yeah.
part and an imaginary part, right? There's the number a plus bi. I go over in the a direction, I go up. I go over a in the real direction, I go up b in the imaginary direction. That point, if you you go down to the origin, meets there at the angle theta.
Which is
All right? And what we know is that A could be considered cosine theta, and B would be considered sine theta. So this number could be thought of as cosine theta plus sine theta times I. You okay with that? All right. Now, if we do the Taylor series expansion of those two things, some interesting cancellations happen. Not cancellations as much as the two series will combine to form the E series.
Wait,
I'll show it to you later.
that with the negative twist.
Yeah, come with questions on Monday.